I'm going to talk to you today about a new kind of number that sounds kind of audacious, and I am pretty excited about this. I've talked about this before, so you have some inkling of what I am discussing. There are 45 slides, and I'll try to keep my pace and do this in 45 minutes, and then have more time to discuss and answer questions at the end and not run over. I'm going to give you a preview here. I'm going to propose that probability is not a scalar. We already know that it's not a scalar in many areas of physics where we look at it as part of a vector, like a wave function that's going to be transformed by some group. I'm going to propose a method called managing logical and numerical uncertainty, both of those. It's different from fuzzy set theory, and I'll show you how. I'm going to generalize Boolean logic by replacing the ones and zeros, the logical bits that stand at the foundation of our number system, with a Markov group representation that has probabilities that it uses. And we'll use that system to propose a new kind of number, and that's going to generalize the existing numbers in a smooth way, and I think that's very important. We'll rebuild mathematics with those numbers, not all of math, but at least addition and multiplication. I'm going to show that these new numbers encompass all probability distributions and manage uncertainty. That's a much stronger statement than you might imagine. And it's stronger because I'm saying that there's a number that can actually contain a probability distribution. And you will say immediately in your mind, oh, wait a minute, that's insanity because a probability distribution is a function. And we're talking here about a number. And I will show you what I mean precisely by that. I'm going to discuss computer and quantum theory applications for this. The problems. What problems are we faced with? Well, mathematics really doesn't have a closed, complete system for managing numerical uncertainty. We have about 3 different levels of this. We have our first level where we can say, okay, let's round these numbers. This is how we teach undergraduates to round numbers and deal with uncertainty in laboratories. Then we have a better way. We can do what most of you do in your research and do a Monte Carlo calculation, taking all possible projections over all possible probabilities for a scenario such as an experiment. Or we can do something that's even more advanced than that. There's a special group of people, primarily in engineering, that look, and in statistics, that look at special types of distributions and how these distributions can be folded together to manage error. However, these distributions are not numbers. And if you think about it, when we look at uncertainty, we're taking a number and saying, well, it has an uncertainty. Suddenly that thing is a function. It is a distribution. It's no longer a number. And these things are distributions, and they don't close back into numbers because they weren't numbers to start with. And so we have a dilemma there to begin with. Computers don't deal well with approximate data unless they're explicitly programmed. Computers very often will take 3 times a third and say that's not equal to 1. So you have to be careful in the rounding and everything else. All observations and data are estimates. They're not real numbers. I contend to you that no person has ever measured a real number in the history of mankind. That would entail an infinite number, infinite amount of precision, infinite data, and you couldn't even store the thing in the entire universe. Pharmacy, medicine, finance, engineering, even physics, we all use approximate numbers, everything that we do. Mass, length, and time are never observed as real numbers. We impose this concept of infinite divisibility because we don't know what else to do, and the real number system works really well. Problem is, how do we begin? To incorporate numerical uncertainty is to incorporate probability. Obviously, if we're going to leave ones and zeros, which are the foundation of information, we're going to look at probabilities of things. But they don't really, they don't combine very well with each other. How do you deal with a probability? How do you form a mathematics with that? Well, you're dealing with a function that's between 0 and 1, or a distribution, and you're going to combine that with another distribution to end up with some distribution. But what's the mathematics? What are the operations and so forth? To have uncertain numbers suggests using uncertain logic. Since our numbers are built upon Boolean logic, we might look there first. But these probability functions don't close nicely because they're distributions. And here's what I thought of 8 years ago today. My work with Markov transformations suggested to use a representation of the Markov Lie monoid, which is a group without an inverse, which is a pair of numbers here, but we'll later see that this can be a vector of any size, to use this set of numbers to generalize 1 and 0 to continuous probabilities. Those probabilities are now going to be part of a group representation. They'll no longer be a scalar. Where we previously used a probability, we now basically are taking, in simple terms, the probability and 1 minus that probability as an object, which is a group representation. We're going to deal with that pair and multiply those together and form a mathematical structure with those. So cutting to the chase, I don't want to do the mathematics, the hard math first. So let me just jump into what we are postulating. I'm going to postulate that this pair of numbers is the fundamental logical entity. It's to be the probability to have a 1 and the probability to have a 0, respectively. Therefore, x1 plus x0 is 1, and they're both non-negative. Okay? These bit vectors, and I'm modeling this after spinors, which is a representation of SL2C that we often use. And you recall that a spinor has 2 components, or maybe 4 components in the case of Dirac, but it's still not a vector. That's why we call it a spinor. A vector would mean that it transforms a certain way as the x, y, z, and maybe x, y, z, t transform, and it doesn't do that. It transforms under another group. And that's why I say they are not transforming under that group, or the regular group, or the Lorentz group. They transform under the Markov group. And so I call these bit vectors bitters.
What is x0?
It's the probability to be false. It is 1 minus the probability to be true. So if I know x1...
What's the relationship of x0 to x2?
There is no x2. I'm sorry, typo. That's an x0 there. A typo, thank you. Representations of all integer dimensions exist, so we can have real long ones. And what are these representations of this group? They're a decomposition of unity into a set of numbers that are non-negative and that sum to 1, sum to unity.
In the case of only a pair, x0 doesn't add any information to the...
It does not add any information. It's exactly like x and y when we do a rotation. And that's a good point. Because if we do a rotation, we always write down x and y, whereas we would only need to write down r and theta. And since r is invariant, then we could say theta goes, such and such. But we write down x and y because it gives us a different type of sense. And we'll show how that works here also. In fact, since we're looking at transformations that leave x1 plus x0 equal to 1, that's the equation of a straight line. And if you imagine an axis like this, where this is x and this is y, you're looking at a line that crosses the positive quadrant. And what we're looking at is this group of transformations that moves you along a line that keeps you within the positive quadrant. Therefore, it's not a translation. And so it's kind of like a unitary transformation maintains x star or psi star psi, and a rotation would maintain x squared plus y squared. This transformation is maintaining x plus y, or x1 plus x0. So the technical group theory we'll get to later. Okay, so without any mathematics, we don't have anything but a definition. So now I'm going to define, we need to define the Boolean logical operations. And so I need to be able to combine 2 of these bitters and form another one. And I need to combine them with all the different Boolean operations, of which there turn out to be 16. And, or, not, nor, exclusive or, equivalence, and all the things that you get with not in those, like not and, which is the NAND gate in electrical engineering. And I'm going to form a product, and since I've only got 2 of these and 2 of these, the indices go over 1 and 0, ij and k, and here's zi, and that's equal to a constant c ijk summed over the repeated indices xj and yk. So probabilities multiply, I multiply the probabilities, and this alpha here stands for the, from 0 to 15, all of the different logical operations that we might have. For an AND operation, let me write it out and it'll be more obvious. The probability to be true, the probability that it rains both days, is the probability that it rains the first day times the probability that it rains the second. That's false if it rains the first day and not the second, or doesn't rain the first and does rain the second, or neither rains neither day. So there are 15 other Boolean products, and they're all permutations of separating these 4 terms, which is this term right here, and these 4 terms here. The logical operations are the ways to separate those 4 terms into 2 categories and put them all in the top, all in the bottom, 1 of them in the top, 2 of them in the top, And the ways that I can do that form the 16 operations. And it's very simple once you realize what that is, that I'm following standard probability theory. Not is a unary operation, and it reverses the bidder and takes the upper into the lower and the lower into the upper. It's easy to confirm, and very quickly you can prove that Z is a bidder if X and Y are bidders. Of course, I have closure there. And that, of course, occurs if you take that term, if I take Z1 and add it to Z0, I'm adding those four terms together. So I always have something that's non-negative, and both terms are non-negative, and both of them sum to unity.
It's the product of two sums, so it's one.
Huh?
It's the product of two sums.
The sum.
Yeah.
The sum of all four of these is always unity. Okay, now having defined the product of entities, we can ask if a sum can be defined, and the first thing is, of course not, because probabilities don't add well. However, it turns out, with a little thought, a weighted linear combination, A1 times, and this is a different index. This is a bidder number 1, a bidder number 2, a bidder number n. If I have n different bidders, and I take a linear combination of them with these coefficients A, which are real numbers, then xi, whoops, I've got a mu there. Oh, that's okay. I've got a distinction between the I and the j here and the mu here, but you understand that that's the same index. If I sum over that, if the A is a higher dimensional bidder, meaning what? All the components are non-negative and they sum up to 1, then in fact this object is an object which is a bidder having two components that add up to 1 and are non-negative. Basically what this is this operation is like a weighted average. And you know, when you do a weighted average, the coefficients have to add up to unity and have to be non-negative.
The products in the previous, those are the products you
Yeah,
just-
that's a number times the first bidder, so that's a vector. And that's a real number times another vector or bidder, and so forth. And if
I don't understand. The real numbers exist?
yeah, the real numbers exist. Yeah, we use all of the numbers. We're going to come back to that.
So
I haven't
this is
thrown-
not the bidder product that you just described.
No. This is just a real number times a bidder.
So
3.2
the n tuple x1 to xn is just vector.
Yeah.
And the a's are supposed to be the basis elements. A's are supposed to be basis elements.
Yes.
It's a representation of a vector.
Define a bidder number to be the outer product. I'm now going to numbers. We've done a logic. So what do we have with our logic? We have two operations. We have 16 products that are distinct, and we have one linear combination. And that's our new mathematics. And we're now going to define a bidder number to be the outer product of these Markov monoid, which are usually two-dimensional representations. And so we're going to take all these things and just have an outer product. So our new number is a group theory representation, just like if we were taking spins of particles. And those of you who have done something with quantum computing know this would be similar to taking the spin of particle 1, the spin of particle 2. If I had 50 of these, I just take the outer product of all of these. And this is, again, a representation of whatever group, like the rotation group that I would have. It's just many-dimensional. And so that is what I have. And now this number is a group representation space. We only really need to write the top one of those, but we're going to mathematically operate with both of them. Remember, the bottom one is 1 minus the top one, but we need both of them in order to make the mathematics work. As error is always limited, we only need a few digits to represent the probability, because it's never known exactly. This is a very subtle point, but if I said the width of this room is 12.32 feet, give or take 0.00596832143938, you'd say, no, that's ridiculous. Error is normally only given to 2 significant digits. You could push it and imagine you had 3. You might even say I've only got really 1 significant digit of error. But I've got some amount, we call that the basis that we're going to have for our error. And normally that would be something like a binary number based on 128 or 256, meaning that when I look at this number, it's that fraction of a binary number that size, and you have to imagine the decimal point there. And so it's a fraction. It'd be like 0.5 or could be up to 1. But this number here, when I write a 1 here, that means it's 1. And you can see I've taken this bidder here and represented it over here. So if I just have a 1, then that represents a normal binary 1, a 1, a 0, a point, a 1, just like here, and I don't need the parentheses. I only need the parentheses when I'm encompassing a binary number. So basically I'm using two symbols, the parentheses and a 1 and a 0. The parentheses are needed to separate out each one of these separate bidders, which is the top piece of the pair. And we know what the bottom piece is. It's the thing that would add to 1 with a decimal point put in there so that it normalizes properly. Arithmetic. How do we define the arithmetic? Well, we know how to add bits. 1 and 0 is the same as 0 and 1, which is 1. And 1 and 1 is 0, and 0, which is equal to 0, except I also carry. Now, what is this operation? This operation is an exclusive OR. And so we know how to define the exclusive OR. Z1 is an exclusive OR, is the probability that Z1 is true and Z is true and Y is false, or X is false and Y is true. That's an exclusive OR. So that's the way we define it with the two components. And the probability that you get 0, in other words, you fail with your XOR, is a probability that both are true or both are false, exactly like you would have here. Then you have a carry digit in addition to that. And the carry digit says that you've got a Z1 in the next place, and that's going to be true only if both of them are an AND. So it's a Z1 is equal to X1 and Z1 times, X1 times Y1 for the AND. And so that gives us our carry operation. Once you do that, then you can figure out multiplication and the other operations, so I don't need to go through that. We can look at Shannon's definition of entropy or information. A more useful form for us here is actually Rainey's entropy. And it turns out that it's already in the equivalent operation in logic. And these two definitions of information are very close mathematically. They do differ a little bit, and we'll show you the advantage of that. If I look at this term right here, x1 times x1 plus x0 times x0, it turns out to be self-equivalence. I can also look at things like mutual entropy, which is the product of two bidders, whether one is equivalent to the other, but I don't have time to go into that. So if I take my information as the definition of log base 2 of 2 times that, then you'll find out that works really well. If my probability is 1, if I have one bit, then x1 is a 1 and x0 is a 0. So I get 1 squared times 2, log base 2 of 2 is 1, and I have one bit of information. Likewise, if the thing is false, then I get x0 is 1, that's 0, so I get 1 squared times 2. Again, I get one bit of information. If I have half and half, then I don't know. It's like flipping a coin. I don't know whether I have a 1 bit or a 0 bit, so that's no information. I would have 1/2 squared, and 1/2 squared is 1/4 plus 1/4, which is 1/2. 1/2 times 2 is 1, and the log of 1 is going to be 0, so I have no information. So just showing you that this Rainey entropy matches the boundary conditions of what we expect for bits of information like with Shannon. And the information content now in an entire bidder number becomes the sum of the information in each bit. So now, believe it or not, we've really made some progress here, because now I've got a number, and it can have all kinds of fuzzy uncertainty in it at different places. And I can go through and I can say, add up the information in each of the bits and use this formula here and get the total. And of course, it will give me the total information that's there. This is a comparison between a Shannon and a Rainey entropy, and you can see they match at the boundary. They're a little bit different in between, but they're pretty close to one another. Bidder operations and numbers are smoothly reducible to the standard numbers when the bidders are 1s and 0s. So if I go back and I take extremes where all the bidders go to 1s and 0s, the probabilities are definite, I get exactly our current mathematics, exactly our current addition, multiplication, and so forth. Specifically, the bidder structures and all the Boolean logic is exactly the same as the truth tables. The bidder structures extend the Boolean logic in binary values, extend the integer, the rational, the real, and the complexing numbers with all the existing mathematical operations as a special case, because I can build everything on addition and multiplication. So in summary, we have new objects, which I propose to be numbers. They're Markov-Lie monoid, or group, if you wish, representations. And we have a generalized logic defined by these two-dimensional objects called bitters. There's 16 different products where alpha goes from 0 to 15. And then here we have a linear combination, which is a weighted average. And to the best of my knowledge, this is a new type of mathematics, 16 products, one addition, and a smooth generalization of weighted math.
So when you have a linear product, linear combination, A1, X1, so on, does the A1 multiply both the components equally?
Yes, yeah, it multiplies both components.
And A1 can be any number?
Any number between 0 and 1, such that all the A's sum up to 1.
Add it to one.
And so that then you can see, well, if the pieces are summing each to 1, and the thing that I'm multiplying sums to 1 is non-negative, then the result is going to be two things that are non-negative and sum to 1. So it's going to constitute a new type of structure there. Now, let's look at some examples. Look at a number 110.0. 0.5, let's suppose I don't know anything else about that number. So I have unknown, unknown, whether it's 1 or 0, true or false, all the way to infinity. If I do that, I can say, what is the lower bound of that type of distribution? Well, the lower bound could be where all of these 0.5s are zeros. Then I would get the number 110.000 to infinity. The upper bound would be 110.0, where I have the 1s all the way to infinity. But if I look at this number right here, you'll notice that that number is infinitesimally close, truly infinitesimal. Only a 1 at the quadrillionth place would need to be added to round that off and put a 1 in the next place and then have zeros. So basically you can say they round to 110.0 and 110.1 with a uniform distribution, which is a square distribution in between. So this object right here, with this iterated to infinity, is literally a square distribution. It comes along, if you plotted it on a scale, it would be flat, 0, out to the number 110.110, and then it would go to 1, drop down, and continue to 0 for the rest of infinity. So I can make that little square pulse, so to speak. Another example is something like this. And if I look at this, it's really a strange number. Here's the binary number, and it's like an Egyptian tablet, and I've uncovered it, and the sand has eroded, whether this one digit, how many things of wheat the Pharaoh got, has eroded it, and I don't know whether it's a 1 or a 0. So the number is either 100.010 or 100. Typo. Sorry. Second typo. There's supposed to be a 1 right there. Imagine that that's a 1. So it's a distribute. It's either one of those numbers, but it's not in between. So if you think about it, the distribution has a probability of 50% to be one number, and then it goes flat, and over here it has a distribution of 50% to be another number. So now we have a number that can be a distribution that's just 2 points. Now if I add the tail on, I can have this one as a tail and this one as a tail. I don't want to bore you. Everybody would be asleep if I went through this, but I can assure you that I can make any distribution of probability to any desired degree of accuracy, no matter what the form, as long as it's bounded by 2 real numbers. Distribution, so the integral or the sum, those would be 1. Okay, so
Can you not do any unbounded
they're bounded automatically because we put these constraints on these letters. We could multiply the real numbers that would take it out. And they're also positive definite. They're probability distributions. And you'll notice probably some of you are thinking that maybe no more mathematics. This looks kind of like wavelets, and I think there's a tremendous analogy to wavelets. They're like little packets with distributions in certain places. But if you think about the things like the Haar wavelet and so forth, then you know that it has a negative region. And these are all probability distributions, so they're all positive definite. I'm going to go pretty quickly through some math. Regrettably, I don't know what slide I'm on, so I don't know how I'm coming. If I look at diffusion, all diffusion can be represented by Markov transformations. And the diffusion represents increasing entropy and loss of information. So a study of Markov transformations is a good way, in fact, the only way that I know of to study probability, entropy, and information all together in one place. And since the diffusion and Markov transformations can't be undone, they can't have an inverse. And I think that was the reason that originally people didn't try to use group theory or Lie groups to study Markov transformations. If you spill the wine on the rug, you can't undo it. However, what I did was I got rid of the positive definiteness, applied the group theory, obtained groups of transformations, and then I removed the identity. So I got this monoid, which is a Lie group without the inverse transformation. So I can use all the power of Lie groups. And we showed that there was a deep connection then between Lie groups and Markov transformations. We did this a long time ago. And I did this as a part of an article in the Journal of Mathematical Physics on decomposing the general linear group. And I showed the general linear group, of course, can be represented as a linear combination. If I have an n by n matrices, since this is n here, and these are going to be n by n matrices, all of those matrices can just have a 1 in one position and 0 everywhere else, and that forms a basis for the matrices of size n squared. That'll form a basis for that group. They're not very interesting, though. There's a much more interesting one that I can make, first of all, by taking the ones on the diagonal that only have a 1 in one place on the diagonal. And those transformations form an abelian group of order n, meaning they're just nothing but, if I expand it according to an exponentiation, they become e to the lambda times that one axis. So it's a scaling on that axis that either makes it longer or shorter. So if I'm in 5 dimensions, then the third dimension would scale it out or scale it back in proportion to what it is. That's one group. It's of order n. Then I can take the rest of the transformations and I take a 1 in any position and a -1 on the diagonal. Therefore, all such matrices have rows that sum to 0. So 1 at one place, and I go down to the diagonal, I put a -1 there, and I put zeros everywhere else, and I take linear combinations of those matrices, and any linear combination of those matrices will give you a Markov transformation. So the abelian group simply multiplies an axis by this e to the alpha, and the Markov transformation looks like this. It basically constantly gives a fraction of something to somebody else. So for example, I could constantly give some fraction of the money I have with me to Carl. So I give him 1% of my money, and I'll give him another 1% of my money, and then another 1%. And I would exponentially lose my money, Carl would gain it. If you look at that, when alpha is 0, that becomes 0, and this is 1. So sure enough, it goes back like a Lie group should, connect with unity at alpha is equal to 0. Now that transformation always preserves the components of a vector. So the sum of the x's is equal to the sum of the x primes. Those are just two vectors there, not bitters. But they could be bitters. However, if they're considered to be probabilities, then they have to be non-negative. So what we have to do, if you look back at that last transformation, the last transformation cannot have a negative alpha. If it had a negative alpha, this term could be huge, and this term would be 1 minus 8 million. So therefore, when I took the linear combination, I would have this debt to Carl rather than transferring money that I actually had. So by using this exact basis for the Lie algebra, then you exactly get, when I have positive parameters in the expansion of the group, you get all the group and no more and no less. And so that's why you lose the inverse. And if you do that in 2 dimensions, here I've got that x1 and x2 again, I apologize. They sum up to 1, and basically what I'm doing is I'm moving in the positive quadrant, as you would see it. Here's the positive quadrant. I'm just moving around in some exponential transformation along that positive quadrant and never take anything inside to the outside. All the power of continuous groups can be used with Markov theory, and now they can, these actions, these Markov transformations, generate the non-negative combinations, and they give me diffusion. So for example, here's one way you say, what does this have to do with the real world? If you imagine an aquarium, and you picture water in a tank with a membrane in the middle, and I put red water on one side, clear on the other, and then I punch a hole in between. It's this transformation, continuous transformation, that moves the red water to the clear side and the clear water to the other side. And so continuously, these progress until finally at some point, you don't know which was originally the red and which was the clear side. Then you've lost your information. This is exactly what you're doing on the bitters. You're taking the probabilities and moving them closer and closer to 0.5, 0.5, so you can have a loss of information and a measure of information in the whole thing. The infinitesimal generators, there are two of them, and it's kind of an interesting Lie group. It is the smallest Lie group that exists. It's not trivial. In fact, if I take L12 and L21, you can check that the commutator is L12 minus L21, and you can do a little linear transformation and show that's the same as the algebra. A commutator with B is equal to A. There's nothing simpler than that. In fact, when we look at the Heisenberg algebra in quantum mechanics, we have the commutator of X with P is equal to actually capital I. And so there's actually a third element there, which has the eigenvalue h bar, but there are three elements to that. If we look at angular momentum, we have Jx, Jy, Jz. There are three elements there. Here we have actually two of these. Now here's an interesting thing. Any power of any combination of the L's turns out that it has its columns summed to 0. What does that mean? That means any power of any element or any element with any other element is in the Lie algebra. That means any analytic function of the elements of the algebra are back in the algebra again. And for those of you who know Lie algebras in the groups, it means there's no Casimir operator. There is no J squared. There is nothing like we have in SU3, where we have two invariants that are analytic functions of fundamental invariants. No Casimir operators. So you have no irreducible representations that separate out. Here are two of those transformations. I exponentiate this one with S and this one with S. And this robs Peter to pay Paul, this robs Paul to pay Peter. And it's a diffusion operation that goes one way. And you notice that it gradually transforms a fraction of one of them into the other one. But I can invoke both of those at the same time, which is like the aquarium, and say, let's go with T and do a diffusion of the aquarium, each part going to the other one. And this is what you get. And the neat thing about this is you can do it in n dimensions and predict things like populations. If you knew how many people were leaving New York and going to California, and the fraction of people leaving California and going to Nevada, and you knew all those cross populations, you just put it in a big matrix, take the diagonals, make the diagonals the sum, the negative of the sum of the other elements, exponentiate the whole thing, and that transformation is your Hamiltonian or your population dynamics for the United States. And if you want to know your stable population, take your eigenvalues of that, and it'll show you exactly what your final population is.
In fact, there exists an analog of the Baker Hausdorff and Campbell and Hausdorff type of identity for this kind of algebra.
So the process, I think I hit one slide, is basically rob Peter to pay Paul. We can begin with, I've already discussed this. Eventually we can't discern who had the greater amount of money if we do an equal transfer there, so we lose our information. The general linear group contains two Markov transformations and two transformations that scale. And while the diffusion conserves probability, because it conserves the sum of the two, it doesn't allow for growth and decay. But these two abelian transformations do. So you can say, hey, your population model moved people from California to Nevada and everything, but they didn't let people get born or die. So what do we do about that? Well, we use these other ones that exponentially, in an exponential fashion, allow us to increase or decrease the population as the birth rate over the death rate, and therefore the general linear group will monitor, even with birth and death rates, that entire thing. You recall I gave another talk, and I don't have time to do that today, of course, and buried in this, that every one of the generators in the Markov Lie group is one-to-one isomorphic to every network that exists in a topological sense. And so one can study all networks by looking at how they correspond to these Lie groups, which in turn correspond to this diffusion. And so that's what we did in another study. Now we can be more general now and say, let's I've lost my light. We can see what we would do if we added in these two transformations like this. And then this is the most general transformation we have that is part of the general linear group. And you can actually look at it. It's, of course, since there are just a certain number of parameters, it turns out that this is like a harmonic oscillator. But it doesn't have the normal sines and cosines because you can have growth rather than friction and everything like that. So it's totally general. But that's the most general solution. And what I really wanted to do is not spend a lot of time on that. I gave a talk several years ago on this, and I looked around and not even 50% of the people were awake. So what I want to do is tell you about some of the things that I've done with this in the meantime. Since these bitter numbers are Markov group representations, I think it takes us closer to a true theory of measurement with information over time. I'm going to explain what I mean by that. One thing is, let's imagine that we have information as a binary number that's recorded out with so many digits. And we know that over time, we're going to gradually start losing that information. How might we represent it? The answer is, if we use a Markov transformation acting upon each one of the bitters with a time coefficient that is dependent in how far I am out in the string, then it will decay that last bit, then begin decaying the next bit, and do that in any combination of ways that we would choose so that our information is gradually degraded. So you can do this kind of neat stuff, like if you had an instrument that was gradually magnetically losing the spins out here, you could say, well, I'm losing this over a period of time due to stray magnetic fields. Then I could model this exactly with these groups. One of the most interesting things is what I call the path dependence of computation. We're all familiar in physics with non-conservative forces. A non-conservative force means if I want to drag this computer down to the other end, it means it's path dependent because I've got friction. There's a difference in taking it along this path and taking it along another path. It turns out in mathematics there is no difference in the paths. Any way that you combine the real numbers, as long as you're careful enough and maintain infinite accuracy, then you're going to get the same answer at the end. Here you do not. In fact, I did a calculation, even just with two bitters, and showed that z times x plus y, and compared that to z times x plus z times y, and you get two different answers. And you can actually measure the loss of either Shannon or Rayleigh entropy by combining them in these two different ways. Now what does that mean? I can't prove a general theorem here, but as you move through, this algebra is non-distributive at this point. I mean, your arithmetic is non-distributive. And therefore you have to be very careful. What you want to do is you want to do your computations in a way that maintain the maximum information. Of course, every carpenter knows this. If I take and measure the length of the table and then add the length of another board, then go off and I take that board and I bring it back and then I subtract that length, I'm not going to get exactly the original length of the table. So we know that compounding fuzzy numbers or uncertain numbers gives us problems, so we don't get closure. In fact, in this whole theory, you do not have an exact zero or an exact unity for multiplication. You lose those because of the distribution that's there. So information loss is path dependent, like friction with non-conservative forces. And we seek to use the path of minimum loss, and we'd like to know what that is. So I've been trying to prove some theorems on how can we be certain that the path would be constituted in this particular way, and so forth. A new world of computing. This is one of the reasons down deep that I wanted to work on this whole thing. If we have a decision process in computing, the basis of all of our computing is basically it's going to come down to if x is greater than or equal to y, then I do one thing, do A. Else I do B. So I make some kind of comparison. Well, with numbers or with strings, that comparison is always unique. So I never have a bifurcation that's problematic. However, here it's possible for the distributions to overlap. Therefore, there's a certain probability that x is greater than or equal to y, and a certain probability that it's less than. So what I must do here, this sloppy way, would be just take the most probable. But that's not how we think. And what we would like to do is model a thinking process a little bit better here. But what we want to do is we spawn two threads, exactly like creation operators in quantum field theory. So we have A daggers here that create one thread that's going to do A, and it carries with it the probability that A is correct, that that condition was correct, and B carries it. And then you have another thing that spawns another one. And so pretty soon you're going to be filling up 1,000, 2,000 threads and all these processors running simultaneously. And then you want to do, naturally, what we do intuitively, is throw away the things that are very improbable. You drop those off, renormalize the sum, and when you end up, you take all this thing, sum it together, and end up with one answer. Probabilistically weighted according to those weights. That means that each decision can spawn into two threads, and so forth and so on, just like particle creation. You get them all back together again. So I think it's a totally different way of computing, and we are in the process of building those kinds of things. Application to multiprocessors. I can't imagine we need a probability less than 0.1%. So probably 1,000 processors would keep us at least modeling all processes that were down to 0.1%, since you have 1,000 of them. And so that way it would be a way to automatically manage the distribution over multiple processors, which is problematic in general mathematics. And so this would be automatic. It would collect it all back, and so we'd have our new laptop would have these 1,000 processors, and it'd only be running one program, but it'd spawn these processes over the different processors. The next thing is then you would take the databases and scientific and engineering values that had uncertainty, which is everything, coefficient of linear expansion, Young's modulus, bulk modulus, the speed of light, the Rydberg constant, and you put them all in, but you put them in a different way. You put them in with a notation. It takes something totally new here. You put them in with a notation with bitters of where the uncertainty is.
How would you put electronic charge?
Electronic charge, you put it in, just put the electronic charge in. It's a binary number.
It's -1.
Huh?
It's -1.00.
Or you can put negative numbers in. I mean, you can handle negative numbers with this.
Joe, what I meant was it has no uncertainty.
Neither does the speed of light.
Oh, if it's -1, but it's, okay.
No, I mean,
The -1 doesn't have an uncertainty, that's correct. So that's exact. Oh, it handles ones and zeros. It handles all the real numbers. So I can write pi in this system, or e, or any rational number, or 7, the exact number 7, or anything else, or any negative number. So any number that exists that I can write in binary exists in the system.
yeah, the speed of light is a silly part because the speed
I
of
could-
light is stays.
Yeah, you're going to tell me to write it as C.
Population.
You're going to tell me to write C, right?
Yeah, no.
Yeah, -1. Yeah. Minus 1 for the charge. But anyway, I put these charges in. If I'm going to put in any coulombs, I think I would have a little bit of error out there. Right?
Yeah, no, I was talking about this.
And so the thought here is very far-fetched, but it's very real. This is the mathematics that would take those trillions and trillions of little uncertain ones and zeros and combine them in an exactly logical way and manage the statistics in the background. Manage the statistics. Which means you wouldn't do a Monte Carlo calculation. It'd be multi-threaded over the processors and bring back the right answers. I mean, so if we wanted to know if our bridge would hold up, we'd say, will this bridge hold up when trucks drive across it? And we'd put in how many trucks? Oh, 8 to 13, give or take 10. What is the weight of each one between this and this? What's the tensile strength of the steel? It's this, but it decays over time. And you put all this uncertainty in and just throw it into the computer and let it calculate. And believe it or not, that programming of all uncertainty is a very difficult thing to do. In fact, there was an article, if any of you read Business Week, of looking at the economy. Who was our last Fed Chairman Alan Greenspan wrote an article. And of course, he's trying to protect himself, I think, a little bit here. But Greenspan wrote this article last week, and he said, well, we had all these geniuses in finance that came up with these new instruments that were mathematically structured in terms of risk. And he said, they didn't work. Why did we believe these people who were great mathematicians and fantastic economists but didn't understand the real world? Well, we believed them and we invested our money and now we're broke. Anyway, that's kind of what he said. And so risk modeling is very problematic, as everyone knows. Computer management of uncertainty.
One charlatan writes about other charlatans.
I envision the direct representation of the better logic in computer systems, and this will automate the management of uncertainty. It will replace a regular rounding, Monte Carlo, and some of the use of distributions. Uncertainty could be put on a more solid foundation, although there's still problems here, because I don't know the optimal paths in the mathematical space. And I found someone who's very excited about this, and that's Dr. Ferdi Ponce, Associate Professor in Electrical Engineering. And she's a world specialist in engineering error. And there's a group of people that study these distributions and how to do better than Monte Carlo, and she's one of those people. And so we have been working together, and she's writing a joint paper that's going to be presented at a conference on uncertainty in Italy. And I guess that has to do with the rail and the airlines in Italy. Also because they know uncertainty over there, right?
And don't forget the government.
Yes, and the government. This new math, a bitter number, can express any probability distribution. I have not proved this to you, but I can now prove this. And this is within 3 weeks of now. I can represent any probability distribution that exists to any finite degree of accuracy by using higher order representations to represent the correlations among the bitter products. In other words, I don't just use two-dimensional, I use larger dimensional ones, but everything comes out as we had before, but it's incredibly complex, but I can prove that. The next thing is since these bitter numbers, when they're expressed this way with finite error, that's all I need for this proof, is that the error is finite and expressed in a binary form, then I can prove that the bitter numbers are isomorphic to the reals. Obviously they are, because I'm only putting in this little bit of finite piece in between where the binary numbers are. So the real numbers just get larger, the real binary numbers. So in fact, it's still a real number. It's isomorphic to it.
Okay.
So a distribution then becomes equivalent in the same order of Cantor infinity as a real number does. And that's kind of starting.
Well, it seems obvious that the cardinality has to be the same as the real number.
Yeah,
If
it
they're
is.
isomorphic, that implies a state about the topology. What topology are you using on these bitter numbers?
What topology, in the sense of nearness or proximity?
He's talking about topological structure.
I mean,
The topological structure is that these objects replace the ones and zeros, so in the sense that they represent topologically the sequential powers of 2 that would occur in a measurement.
are you putting a metric on determining how far
Not
away?
yet.
Well, I don't understand what you mean by isomorphic then. Isomorphic is a topological
Means-
statement.
No, it's not necessarily. Well, I can make, if I make a correspondence between the symbol structure in one and the other, you've already agreed that it's the same order of infinity, right?
Yeah.
Okay, but that's all I'm saying. We normally let linear operators act on vectors in Hilbert space, and equivalently or on creation and annihilation operators. And the probability of our distributions comes from psi star psi. Now the eigenvalues, and now I'm leaping into something that's I'm not that confident of. We think that we can do this. Our eigenvalues become these bitters. So the eigenvalues are no longer a real number, but become a group monoid representation. So now if you think about it, all of a sudden things got horribly complicated. Because we're imagining a Lie group acting upon a space, which is a representation space. And we normally have a well-defined mathematical theory of this algebra acts on a representation space and gives us numbers. And Hermitian operators, the numbers are going to be real. And now I'm saying, whoa, what we can do is we can represent that eigenvalue as one of these distributions, like a square wave. The particle was in this box at time t is equal to 0 when we opened it. And so the eigenvalue becomes that bitter distribution. So now the eigenvalue is a group representation itself. And that's kind of hard to think about because the mathematics isn't complete there. And would that work? In other words, we could write out the distribution, whereas normally we get the distribution by looking at psi star psi and saying, what does this probability distribution look like? Now we can actually put that distribution formally in the number that represents the state space. Distribution can be an eigenvalue. Am I using the word eigenvalue correctly? Is there a way to define the Hilbert space so it can have an eigenvalue which is a group representation? I don't know that. I haven't been able to do it. But the quantum states are then eigenvectors, a representation space of the Lie algebra observables. Now these eigenvalues are representation space for the Markov algebra at the same time. So I have not only my x and p and angular momentum and the Lorentz group, I have the Markov group which allows information to degrade or observations to degrade, and that's what I'm trying to get. Is there a way to combine this Lie algebra of diffusion that's classical, that says you're losing information over time or something, or you're measuring something by forcing the particle to be photographed and go through this slit. I'm trying to incorporate, I haven't done it, but I'm trying to incorporate that type of reasoning and thinking into the Lie algebra that has to do with quantum theory with entanglement. So if these eigenvalues are a representation space for the Lie algebra with connecting to information theory and loss over time to measurement theory, can that new marriage give us a deeper understanding of the collapse of entanglement? I don't have time to talk about that a lot, but I don't know a lot yet either. But you can kind of sense where I'm trying to go with that. So these new bitter numbers allow a greater transparency of the information from measurements. We can have an eigenstate of simultaneous knowledge of x and p. Now I hope you noticed that something strange happened here with the second sentence. I'm saying that we can have an eigenstate with simultaneous knowledge of x and p displayed as these eigenvalues. How can we do that? Well, x has an eigenvalue that is only so accurate. The box has a limitation defined by the photon's wavelength, and we only know its accuracy this much. So we are allowed actually to know a lot about the momentum of this electron, and we don't violate anything in regular quantum theory with this. We maintain the uncertainty principle, say we know a lot about position, we know a lot about momentum, and we can write both of those probability distributions which are still the Fourier transforms of one another. That would be interesting. And we now have something where x and p to this order would commute with each other. And that's, of course, an extension of the regular Lie algebra that we had in quantum theory. It doesn't violate the uncertainty principle. I say nothing that changes anything about quantum theory. The Hilbert space, and this is the result that I just got 2 nights ago. I was very excited about it. It was very hard to think about. And I worked on it for quite a while. Like everything, it's always simple after you see it. But I have, with these bitter numbers, I have 2 probability distributions. These distributions can be thought of in 2 ways. One way I can think of them as a function. I know how to fold 2 functions together, like psi star psi. And we know how to do that. It's the scalar product of one function with another. That's the critical thing in quantum theory. Everything rests on the probability that this state is found in this state. It's the cosine of the angle between the 2 vectors in the Hilbert space, the scalar product. It gives us our metric in the Hilbert space because it gives us the magnitude of a vector, which we can normalize to 1, which we assume has been done. And it gives us the angle between 2 vectors, how much of this vector is over here on this vector, like this. Well, my new result is, what I wanted to do was show that, of course I could do that, because I've got 2 functions. Can I do that in terms of bitter logic? Can I do that in terms of and or, and not? And build the scalar product between these 2 strings And now I'm saying that I have a scalar product between two strings of symbols, and that scalar product exactly reproduces what I would get if I took those as functions and folded them together. And you can see that it could be done, but how exactly to do it and how to do the logic took me quite a while. And so now I have a scalar product of two numbers. Now if I have that, is it possible to actually take this and we can make a complex number of this bidder with no trouble at all? Would it be possible to take a bidder and represent the state of a system with it? I don't know, but it's something I'm looking at. Finally, we know that space and time are limited by the accuracy of the measurements that make their infinite divisibility questionable. And of course, here I'm in the philosophical realm, but we can always say we're trying to do something, we're using the real number system, and yet we know it's meaningless to use a real number to measure the position of a particle. Space doesn't have that infinite divisibility, not at least in the laboratory. And so we can say, maybe we have imposed something on our space that's unrealistic. And maybe this is a more realistic way to look at space with these types of more general numbers, to look at space and time and mass and other quantities, certainly in engineering. So there are two ways we can go. We can look at theoretical physics and say, is this showing new light? But we can certainly do the practical things in computers, and error in bridges, and logic in computers, and proceed with that in a very practical way and see if we can make sure that Alan Greenspan doesn't make any more mistakes in the future. And I thank you very much.